So I'm excited to welcome you all to our next session of ICFP. This session is about fixed points, and our first talk is by Sven Keidel, who will be presenting work on big step abstract interpreters and using fixed points there. Sven.
So thank you very much for having me. So this is joint work together with Sebastian Erdweg and Tobias Hombücher from Johannes Gutenberg University in Mainz in Germany. In this work, we describe an approach to modularize the implementation of fixed point algorithms of big step abstract interpreters, which are a type of static analysis. And this is a lot of terminology, so let's break this down and let's start with fixed point algorithms. Specifically, what are fixed point algorithms and why do static analyses require them? When you analyze a program such as this one here, then the result of the analysis can be abstractly described as the solution to an optimization problem like this over a number of inequations derived from the program. And because of language features such as loops and recursion, these inequations can have cyclic dependencies. And the task of a fixed point algorithm is to resolve these cycles and to find a solution to the optimization problem, preferably the most precise solution within the analysis lattice. Now let's come to the modularization part. Specifically, why is there even a need to modularize the implementation of fixed point algorithms? This comes down to the observation that there is no single fixed point algorithm which performs best in all situations, specifically which delivers satisfactory performance and precision for all analysis frameworks or for all analysis within a single framework or even for all programs within an analyzed language. And because of this, analysis developers often create specialized fixed point algorithms for different use cases. For example, the suit analysis framework implements 7 different fixed point algorithms for different types of analyses. 2 algorithms for distributive analyses. 2 algorithms for bidirectional distributive analyses. 2 algorithms for field-sensitive bidirectional analyses. And 1 algorithm for context flow and field-sensitive distributive analyses. Now, more generally, if the implementation of fixed point algorithms is not modular, then it takes a lot of effort to develop and maintain many different versions of fixed point algorithms. And it's hard to reuse parts of fixed point algorithms. Furthermore, analysis developers often feel the need to change existing fixed point algorithms, for example, to fine-tune their precision and performance. To see this, take a look at the changes, the monthly changes in the number of lines of code for different fixed point algorithms in the UPAL analysis framework and the TGS analysis framework over the span of multiple years. And you can see that these fixed point algorithms require constant changes to deliver satisfactory performance and precision. Now, the problem with changing existing fixed point algorithms if the implementation is not modular is that changing the algorithm can introduce performance and precision regressions for some types of analyses. Furthermore, changing fixed point algorithms can introduce soundness bugs, which question the validity of the analysis results. Now, these soundness bugs could be found with a rigorous soundness proof, yet proving soundness of fixed point algorithms is really complicated, and maintaining a soundness proof over long periods of time, over many changes, takes a lot of effort and is often infeasible in practice. These problems can be addressed and mitigated by modularizing the implementation of fixed point algorithms. So in this work, we describe an approach which modularizes fixed point algorithms for big step abstract interpreters. So what are these? Big step abstract interpreters are an alternate big step language semantics. In their simplest form, they evaluate an expression under an environment of bound variables to a value. But because this is an abstract semantics, we use abstractions for environments and values, such as intervals for numeric values, for example. Such an abstract interpreter can be implemented in a meta language like Haskell with a regular recursive function, like in this example here. Now, I don't expect that you read or understand all of this code, but this interpreter does what you would expect. It pattern matches on the expression you want to analyze. Then it calls itself recursively to evaluate sub-expressions to abstract values, and afterwards recombines the abstract values. Now, the problem with this big step abstract interpreter is that it does not terminate in this last case, where we try to evaluate the body of a function in case of a function call. While non-termination is to be expected in case of concrete interpreters, non-termination is really undesirable in case of abstract interpreters. Specifically, we would like the abstract interpreter to always finish and yield an analysis result, deliberately trading off some precision of the result. In case of big step abstract interpreters, termination is enforced by a fixed point algorithm. So let's dive deeper into the reasons why big step abstract interpreters diverge to inform us how we have to design a fixed point algorithm which enforces termination. So in our work, we identified 3 distinct problems which cause big step abstract interpreters to diverge, which a fixed point algorithm has to address. The first problem are recurrent recursive calls. For example, if you're trying to analyze the recursive factorial function, then you obtain an analysis trace like this, which contains a recurrent recursive call. Specifically, the abstract interpreter calls itself, tries to analyze the same expression under the same environment that it has seen further up the stack, and therefore the trace becomes infinite and the abstract interpreter diverges. But even if a fixed point algorithm would address this problem, there's a second orthogonal problem to this one, which is that infinite recursive call chains may not even have a recurrent call. For example, if we analyze the factorial function for negative numbers, so minus infinity to minus 1, then we obtain an analysis trace like this, where the argument to the factorial function shrinks and shrinks and shrinks, and thus there's an infinite call chain of recursive calls, but they never repeat. So a fixed point algorithm has to address the second problem as well. But yet there's a third problem, which is not addressed yet, for which we have to look at the trace of a different function. So for this function, the fixed point algorithm has to solve this recursive equation here. And it does this with a standard process called fixed point iteration, where it applies the equation and produces intermediate results, which are in this example intervals which grow and grow and grow and never stop growing. So fixed point iteration here does not terminate. Because of these 3 reasons, this big step abstract interpreter in this example does not terminate. So let's try to fix this. Specifically, we now use a fixed point algorithm which solves these 3 termination problems. To do this, we refactor this big step interpreter from before and introduce a function fixPhi, which implements the fixed point algorithm. And I will explain this function, how it works in a little bit. Furthermore, we have to replace recursive calls of the abstract interpreter to itself by calls to a function eval_rec, which is the argument to the function which we pass to the function fixPhi, the fixed point algorithm. And this allows the fixed point algorithm to take control of recursive calls. Lastly, we have to change the type of the abstract interpreter to allow the fixed point algorithm to pass along auxiliary data that it needs alongside the inputs and outputs of the interpreter. So now let's dive deeper into the function fix_phi, the fixed-point algorithm, and let's see how it works. Fix_phi is a regular simple function which takes as input the interpreter function, which we have seen before in the example, and a fixed-point combinator which encapsulates the core logic of the fixed-point algorithm. Now fix_phi calls the fixed-point combinator and the interpreter function alternatingly to allow the fixed-point combinator to take control of recursive calls and allow it to enforce termination. So these fixed-point combinators are the core contribution of this work, and they allow to control different aspects of the fixed-point algorithm. For example, the order in which analysis results are iterated on. So for example, if there are multiple nested recursive calls, then the innermost combinator here iterates on the innermost calls first until nothing changes anymore, and then moves on to the outer calls. This combinator also solves the first termination problem I've talked about before by cutting off recurrent calls and to enforce termination. Furthermore, it solves the third termination problem by applying a widening operator to the analysis result to force fixed-point iteration to terminate. Furthermore, other combinators control how deep the abstract interpreter is allowed to recurse. For example, the context sensitivity combinator here introduces artificial recurrent calls by joining calls to the same function if they occur in the same calling context, truncated to length 1. Furthermore, other combinators control what expressions are iterated on. So before you have seen that the abstract interpreter in this example diverged for expressions which are the body of functions. Therefore, this filter combinator applies the argument combinators only if the expression is a body of a function, which is a performance optimization. So now let's circle back to the motivation and let's see how these fixed-point combinators allow us to create specialized fixed-point algorithms. And here we take a look at a little bit larger example of an analysis which applies to a language with functions and loops. And here we can create a combinator expression which applies different iteration strategies for loops and functions and interleave them seamlessly. So let's take a look at the lower expression which applies to the body of a loop. So here this unrolling combinator increases the precision of the algorithm by unrolling the first 10 iterations of the loop and analyzes them separately. Furthermore, if there are multiple nested loops, then the outermost combinator iterates on the outermost loops first. Now let's see how these combinators allow us to make changes to existing fixed-point algorithms. Specifically, we can make changes by adding, removing, or rearranging combinators. For example, we can increase the precision of the algorithm from before by adding this unfold combinator, which always unfolds the first 3 recursive calls, before calling the argument combinator, which decreases precision to enforce termination. Now, we implemented 12 of these fixed-point combinators as part of the sturdy analysis framework. Many of them you have seen already in the examples that I've given before. We've implemented 3 combinators which implement different iteration strategies which describe the order analysis results are iterated on. 2 combinators which allow to mix different iteration strategies based on a predicate. 4 combinators which affect the recursion depth of the analysis. The first 2 decrease the recursion depth to enforce termination, and the latter 2 regain some recursion depth to increase precision. Lastly, we implemented 3 tracing combinators which allow to, for example, record important analysis data like an interprocedural control flow graph. Furthermore, we have used these fixed point combinators to implement fixed point algorithms for 3 different analyses for 3 different languages. Specifically, we implemented analyses for Stratego, a program transformation language, WebAssembly, a low-level language for the browser, and Scheme, a function language with imperative features. We used these case studies to show that the combinators are in fact analysis and language independent and are reusable across many different analysis use cases. Furthermore, the case studies show that the combinators are precise and performant enough to yield useful analysis results for real-world programs. So I won't go into all of these case studies, but I want to highlight the WebAssembly case study. Now, we described this case study in a lot more detail in its own paper, which got recently accepted at eCoop, which I also invite you to take a look at. In this case study, we implemented a constant propagation and dead code analysis for WebAssembly, which can be used to eliminate instructions of the WebAssembly binaries to save space. In this eCoop paper, we evaluated the performance and precision of the analysis by running the analysis on 1,458 WebAssembly binaries of the WASM benchmark suite. The left graph shows the running time of the analysis, where we set a timeout for each individual analysis for each individual program to 60 seconds to keep the running time of the entire experiment within a reasonable time frame. And for this, we obtained an average running time of 5 seconds. The right graph shows the precision of the analysis, namely the percentage of instructions which are surely dead and can be eliminated from the WebAssembly binaries. And for this, our analysis was able to eliminate 20% of the instructions on average, which is more than the industry-leading tool BinaryN, which was only able to eliminate 9% of the instructions. So this case study shows that the combinators are precise and performant enough to yield useful results for real-world programs. Lastly, we have developed a soundness theory for the combinators. Specifically, we showed that each of the fixed point combinators can be proven sound once and for all. And this means that analysis developers don't have to worry about soundness of their fixed point algorithm as long as they reuse sound combinators. Furthermore, we used and applied this theory to prove the 12 combinator sound that we have implemented as part of this sturdy framework. And with this, let me conclude this talk by reiterating the contributions of this work. We describe an approach to modularize the implementation of fixed point algorithms for big step abstract interpreters by the means of fixed point combinators. We've implemented a library of 12 different fixed point combinators and implemented them as part of the sturdy analysis framework. We then use these combinators to implement fixed point algorithms for analyses for 3 different languages, to show that the combinators are reusable and practical in practice. Lastly, we developed a theory for soundness of these fixed point combinators, which allows us to prove combinator sound once and for all. And with this, I thank you very much for your attention, and I'm ready to take your questions.
Thank you very much. We have plenty of time for questions, and we have a microphone over here. It's also possible to ask questions on Discord, and I'll be checking that. You have a question?
Yes. Is it on?
I think so.
Okay. Yeah, so you showed us that the way your approach works is by applying.
Test. Okay, sounds good.
Yeah. Yeah, so you showed us that the approach works by applying the function and your operator kind of alternatively. So you apply the function once, and then you apply the function, your combinator. So does this introduce overhead? And then is there a way you think you can compile this away to eliminate the overhead?
So every time you modularize something, there is the potential to introduce some overhead. And the way we mitigated this is by essentially inlining everything. So we inline the implementation of the combinators, and we inline a lot of the modularization that is part of the abstract interpreter. And then we inspected the low-level code that is generated for the interpreter, and this is very close to a handwritten interpreter that you could have written without all of the modularization on top. So.
If people could give their name when they ask questions, that would be helpful for people online.
Good. My name's Simon Peyton-Jones. I work for Epic Games. So in a compiler for Haskell, we have a demand analyzer that works in a very similar way that you described. But one of the problems about finding fixed points we have there is if you've got a function, and in the body of that function, a recursive function, and in the body of that function is a nested recursive function, then for each iteration of the outer fixed point, you tend to have to, look at the inner function. Are we really going to fixed point all of that? So, and even if you do, then maybe for the next iteration of the outer function, you might start from the point you got to on the inner one rather than starting from scratch. We found that kind of, or you might want to say, well, do one iteration of the outer and only one of the inner and then go back to the outer one. And so that's quite a complicated thing to express. Can your combinators express all of that kind of interaction too?
Yes. So the innermost
Great.
combinator does something like this, and this can be seen in the Fibonacci example that we give in the paper, that it actually first iterates on the innermost calls, and then on outermost calls, and then again on innermost calls.
Sorry, I'm not talking about innermost calls and outermost calls. I'm talking about a function f that has a nested recursive function g, right? So when I'm going to fix point on f, but in each fixed point iteration, I've got to look and find a fixed point of g maybe. That's not like having two calls to f that I explore in breadth first or depth first at all. You see the difference?
Yes. But the combinators handle this part. They alternate between fixing the combinator of the inner function and the outer function.
Oh, okay.
Cool. It depends on which combinator you use. The innermost combinator does that. The outermost combinator skips the iteration of the inner calls.
Okay, well, it's great to hear that you can do that too. That's very, very impressively expressive.
Also, what you mentioned, it really depends what kind of performance you get from that. So in our experiments, we have seen that some of these iteration strategies, like the innermost iteration strategy, works good for some programs, but worse for others. And vice versa, the outermost strategies works good for some programs and bad for others, which reinforces this problem that we are trying to solving, that there is no one single best fixed point algorithm to rule them all.
Hi, Benoît Montagu in RIA. I guess you've heard about the top-down fixed point algorithm. So it's a fixed point algorithm that is very efficient because it tracks the dependencies between the different calls of your functional f, so that it avoids unnecessary calls to f, which saves a lot of time in practice to run an analysis. So that's one of your fixed point combinators also tracks these dependencies to avoid unnecessary computations.
Say again, what dependencies are tracked?
Dependencies between different calls of the functional f that is passed to the fixed point solver.
Yes, so some combinators, they track dependencies between analysis results. Specifically, the innermost and outermost combinators, they track which recurrent calls depend on other recurrent calls. And this allows the combinator to decide how much it needs to recurse before cutting off recursion and where to iterate. So this combinator does this dependency management you mentioned.
Great, thanks.
So we have one question from the Discord, which is Edwin Turok asks whether you have combinators that are involved in do narrowing rather than widening.
So we have not considered narrowing yet. We only considered widening. To give some context, widening computes an upper bound of the analysis result with the previous result and ensures that an ascending chain of these results terminates. Narrowing is the opposite concept, where you start from a call and you create smaller and smaller calls to improve precision, but we have not considered this case yet.
Okay, any further questions? Over there.
Pass. So it's not obvious from your examples. If your evaluator is written in CPS style and every branch of the pattern matching is calling back to something that looks like a fixed point, but most of the time it's not, how would you express that in the fixed point to say that most of those calls are not really recursive calls?
So I think I don't understand your question. What do you mean with CPS style?
So if the interpreter and not the language below is in CPS style, everything, going to next instruction is calling the continuation of the interpreter itself. So you're going back to the fixed point combinator in that case, I suppose.
Right.
And is that going to find the white places to apply the fixed point and the white places to just continue and not abstract?
The big step abstract interpreters that we have implemented are not implemented in CPS style, but in direct style, where you recursively call the abstract interpreter. And we have not considered other styles of abstract interpreters that would describe the CPS style. So I have not thought about this, but let's discuss this afterwards, maybe.
Okay. Let's thank Sven again.
Yep, thank you very much.